This is a Lowell Observatory podcast.
5, 4, 3, 2, 1, 0.
Welcome to Starslip, a space oddity.
The Eagle has landed.
Hello and welcome to our latest episode of Star Stuff Podcast. My name is Kevin Schindler and I'm the historian and public information officer at Lowell Observatory. And I'm joined by Dr. Melodie, my colleague here at Lowell Observatory. She's one of our mission scientists. And our guest today is Rusty Schweickart, Apollo 9 astronaut, and really a leader in looking at the future of our planet and keeping it in a good place, I think.
Is it getting lost?
Figure out making it sustainable. How about that for down the road? This Rusty, you joined us in a past podcast.
Yeah,
and we talked a lot about your Apollo work, and so we thought we'd do a little bit more modern stuff.
All right,
we talked about that some, but I know Melodie, you had a question before we start, just about B612 and what B612 is.
Oh yeah,
and how you got involved with that. So,
wait, you mean if he funds?
Yeah, just generally who they are, what B612 is. And
okay, yeah, I was curious, what role does B612 have in preventing asteroid impacts, and then how involved are you guys in funding active research?
Well, we're being funded to do active research, so
Got it.
We're hopefully the doers rather than the funders. Although we love the funders that enable us to do work. Actually, what I'm going to do is recommend that you talk with Ed Liu about that. He's the one of the co-founders of B612 Foundation, but he's the one today leading the effort as the head of a subunit we call the Asteroid Institute. It's one of the elements of B612 Foundation overall. But Ed is leading the technical work with a whole system called Atom, which we've developed, which is basically shifted the early work we did in B612 from the question of discovering and deflecting asteroids. And our primary question then was, can we deflect, and how do you deflect, and what's involved in that? He shifted the work once we kind of academically solved that problem, not physically, but academically. Ed sort of shifted gears of our B612 work to research on improving the discovery rate. And so he's done a lot of work, which is developed new tools, which are publicly available, whereas NASA kind of keeps fair control of their tools, which are in the discovery process.
Were you guys involved at all with the DART mission?
We were not involved directly in it, but DART actually is, in a sense, something that we advocated for over 10 years before it happened.
Yeah.
From the very beginning, because the initial work when we founded B612 was the fact that more and more near-Earth asteroids were being discovered. But at that time, back in 2000, 2001, really nobody was doing any real work to say, what do you do about it? If we find one that's got our address on it, what do we do? And so B612 initially got together, a bunch of us under Ed Liu and a guy at the Princeton Institute for Advanced Studies named Pete Hutt got together after Ed gave a lecture in Princeton, and they started talking about it and decided to bring a whole bunch of people together to deal with this issue. And the two questions we asked when we got together in 2001 was, number one, is there anything that can be done in terms of human capability to do something if you discover an asteroid that's headed toward an impact? And if the answer to that, after looking at technology and the status of the state of the art, was yes, then the question was, how do we do that? And, we were a bunch of scientists and existing and former astronauts at the time, and a bunch of technical people, engineers, astronomers, astrophysicists, all kinds of people. and a lot of it, all of us had worked or were currently working in government. And all of us are saying, we're not going to be able to talk the government into doing anything. So if it's going to happen, we've got to do it. So we formed a 501c3 nonprofit foundation to say, okay, we're going to tackle this issue of how do you handle the knowledge that an asteroid is headed for an impact. And that was what we worked on for about 10 years while I was leading it. I had retired at that time, but I devoted my time to running that organization for the first 10 years. And then we sort of got to the point where we learned about everything hypothetically that you could learn in terms of how you're going to deflect, different techniques for deflection, that kind of thing. But there was no way a 501c3 was going to be able to actually test these things, right? So, what we were doing was beating up on NASA to get the job done, to do the testing. And so DART was sort of finally the first example of that. But we actually had nothing directly to do with DART per se.
But you set the stage for it. And I've had mentors tell me that half of science is the socialization aspect of it to get everyone on board, right?
Well, it is. And DART, of course, was a very, very interesting mission. Again, I don't know how technical you want to get, or what.
Keep going.
Just
Keep going. Okay, stop me if I.
I got the bell here.
Well, the big question, the big unknown from the time we really realized that kinetic impact that is running in, most people are not aware of the fact that what you do to prevent an impact that is going to happen is to actually slightly change the velocity of the asteroid. You don't change the direction it's going, which is what everybody intuitively thinks is what you do. What you do is change the velocity of the asteroid slightly, which then changes the size of the orbit, therefore taking longer to get around the sun or shorter time to get around the sun. And what you do is 5 years in the future, you miss the rendezvous. The Earth will have gone through the intersection of the two orbits before the asteroid arrives, or conversely, if you do it the other way, then the Earth goes through the asteroid, the intersection before the asteroid gets there, and the asteroid arrives too late. So what you're doing is changing the time that the asteroid will arrive at the intersection off in the future when otherwise it would have hit. If you change the direction, you change the use the same amount of energy to change the direction of the asteroid. You might change the impact point on the Earth by 5 or 10 kilometers after 5 years. So, I mean, it's a big difference. People think that changing the direction is the thing to do. It's not. But the big unknown in that process was that when you run into an asteroid, which is kinetic impact, when you run into the asteroid, two things happen. The momentum that you come in with now gets added to the asteroid's momentum. But in addition, things get thrown out of the asteroid, and the stuff that gets thrown out of the asteroid in excess of velocity, in excess of the local escape velocity from the asteroid, becomes an additional momentum change. And what we refer to as the term beta, which is also called a momentum multiplier. In other words, if the momentum you're coming in with is 1.0, then the momentum multiplier might be 2 or something like that, depending on how much ejecta gets thrown out the other way. And, people for years, we didn't have any data on this. Nobody, there was no way it's not something you can calculate because we don't understand the structure of asteroids well enough to do that kind of thing. So that was a big test on what is beta, and if you're going to make it miss the Earth, it certainly needs to be, you need to give it enough of a momentum change so that you don't just change the impact point on the Earth. You want it to miss the Earth entirely. So the question of the value of this term beta was really important. And I was thinking it would be something like 1 or maybe a fraction of 1, a little less than 1. And it turned out that from the test with DART, which was a very clever test to be able to actually measure beta, It turned out that it was about 3,
Wow.
over 3. So 3 times as much of the velocity change in the asteroid that we hit in the DART mission, 3 times greater change was made by the ejecta than was the initial momentum that we hit it with.
That's specific to DART, I mean, to the actual asteroid moonlet that we hit. So,
That's a very interesting subject.
okay, so not necessarily specific, or is it something we
Well,
have enough information to apply it to?
this is a matter of some debate, People like to generalize with data points of 1. You have to be
As an astronomer,
really careful.
we're very guilty.
Right. You got to be very careful with that business. But what we've come to know is that most asteroids of the kind that we're worried about in planetary defense seem to be rubble piles. They're basically very, very loosely held together just by gravity. They have very little internal structure. And this has been true in both landing and sampling missions that we've taken and discovered this. I mean, the one that landed on, I'm forgetting names. I'm old enough that I've lost names. No. Psyche is going to be very interesting because it's probably one of the very few solid, large objects.
Oh,
No,
the
but
one that landed and took the sample.
yeah, that we took the sample. Well, that sample was we thought was going to touch down on the surface and take maybe be able to get a few samples
Yeah.
grab. Well, when we touched it down on the surface, it went in a meter.
Whoa, wow.
I mean, it just disappeared a meter underneath the surface, and then it overfilled the sample return thing. We had some problems because it didn't close tightly afterward because of all of the stuff inside of the sample container. So the fact that 3 times as much of the momentum was created by ejecta says, wow, when we do a deflection in the future sometime, in order to prevent an impact with the Earth, if we use kinetic impact, we're going to have a big cloud of stuff that's generated, and that over time, and you know this as an astrophysicist, over time, as that asteroid continues around after the deflection maneuver, and it may be 3 years before its nominal impact point, over those 3 years, all of that ejecta will string out along its orbit. It doesn't go out radially, forever. I mean, that's flat space. We don't live in flat space. We live in a gravity environment. And therefore, the dispersion ends up being almost linear along the orbit track. Well, what that means is if the main body of the asteroid now ends up going either in front of the Earth or behind the Earth, but not hitting it, there's going to be one heck of a lot of debris that does hit the Earth.
Some spectacular.
Right? So we're going to have a man-made meteor shower, and who knows what the largest size piece of debris is. We really don't know that, and there's no way that we're going to know an asteroid characteristics well enough to prevent that kind of thing. So the unfortunate downside of a successful deflection using kinetic impact may very well be a man-made meteor storm. This is, which makes kinetic impact look a little less desirable. The chief alternative to a kinetic impact is a nuclear explosion. Well, that may be even less desirable. I mean, nobody wants nukes in space or anything like that. So, we've always looked at a nuclear deflection as a last resort if any other technique does not work. But we're looking now at other techniques which would avoid the downside of both of those. And hopefully before we ever have to really use one to save lives or assets, we'll have one that's a little more benign than either of those two.
Well, you've clearly shown the importance of planetary defense, and it's our future of us and future generations, our planet.
Long-term future of sometime, our great-great-great-great-grandchildren may be saying, well, who invented that thing?
Well, and so how do we get that more into the agenda of space exploration? I mean, it's changing, but it feels like, that should be more of a focus.
Well, and it is one of the fundamental things that B612 has always done is to say we need to test these techniques so that we really understand the physics of what's going to be happening, and we need data points more than one. I mean, we sort of conceptually demonstrated in DART that the concept of kinetic impact would, in fact, enable us to change the velocity of an asteroid. But there are other factors. And your question is very interesting, Melodie, because no two asteroids are going to be exactly identical. Not only that, but where you hit on any given asteroid is going to make a difference in what comes off in all likelihood, because there are boulders. We've seen them, when we go to an asteroid, we see. So do you just eject a large boulder and that's part of the debris, which could be pretty dangerous? Or do you have dust? The pro-nuke guys are very positive that if they hit it with a nuke, they can pulverize it to the point where nothing large enough is going to come off to create trouble. Well, can you prove that? That means using nukes in space. That's not something people like to do. And in the end, each asteroid is going to be different, and you may end up blowing pretty big chunks off that are going to be dangerous anyway. So it's a very interesting subject.
How big are the political constraints with planetary defense? I mean, especially when you're talking about nukes, that's like the top of the pyramid, but even like kinetic impact. I mean,
well, the real
charge?
real issue when you talk geopolitics, and by the way, let me just summarize a lot of stuff without explaining it very well, but I'll tell you the bottom line. The bottom line is that the technology issues of planetary defense pale in comparison with the geopolitical issues. Was something that we learned in the process of really studying this. Why a geopolitical issue? Because if an asteroid is going to hit the Earth, what you're doing to deflect it, no matter how you deflect it, you're changing its period such that it arrives early or late. But it has to arrive, I mean, if you look at it, the Earth goes through an intersection of two orbits.
No matter what.
In about 8 minutes. From the time the leading edge gets into the intersection to the time the trailing edge leaves the intersection is about 8 minutes, very roughly speaking. And therefore, what you've got to do is change the period of the asteroid such that its arrival is affected by more than 8 minutes. But if it's less than 8 minutes, it's simply going to hit somewhere else on the Earth.
Yeah.
Well, you may be saving some people, but if you look, the intersection of the asteroid's orbit with the surface of the Earth is a line that goes all the way across the Earth. And so wherever it was going to hit, you can just go along that line one way or the other. And if we don't have a completely successful change of its orbit, then it's going to hit in a new place. Well, there may be 10 countries along that line. And when you go up, when you have to launch in order to get there in time to make the change, you don't know the orbit accurately enough to know exactly where it's going to hit. We're only going to find out once we get there, in general, determine an accurate enough orbit on the asteroid that we can know with much better certainty of where it would actually hit. So most of the time, you're going to get up there to deflect it, and you're going to say, oh, it's not going to hit the Earth at all. The probability when we had to make the decision to launch was 1 in 10. You're not going to let that go. 1 in 10, something big is going to hit the Earth. You're going to try to deflect. You get up there, 9 times out of 10, it wasn't going to hit the Earth anyway. Okay, but the 1 time out of 10 that it was, you better make a successful deflection, or what you've done is hit somewhere where it wasn't going to hit, and that's a man-made thing or human-caused accident now. Well, those countries, how do they decide? Well, if the place was going to hit, if the thing was going to hit in the middle of the Earth, let's say, along of this line, the guys who live over on this side say deflect it that way, and the guys who live over here say deflect it that way, right? How do you decide that? That's not a technical issue. That's a geopolitical issue. The president over here has got a re-election campaign in 4 years when it would hit. Don't drag it over my country on the way off the earth, right? So, I mean, the geopolitical challenges, who does it, who pays, how do you handle liability, which direction do you, all of these things we studied it, took it into the United Nations, and what we came to realize is that the geopolitical challenge, when we're actually faced with a threat, is going to be a bigger challenge, human challenge, to make a decision and take action than the technical issues.
In many ways, I would argue that global warming or global climate change is somewhat of a harbinger of
Yes and no. Some of the things are similar and some of them are very different.
Yeah.
For example, nobody in the world has to change anything they're doing to have a successful deflection of an asteroid.
Yes.
Everybody in the world has to change what they're doing in order to have it successfully address climate change. So, I mean, there's one big fundamental difference right
So
there.
you feel more hopeful that people will come together for deflecting an asteroid?
Well, and there's the other thing. An asteroid deflection is a sudden thing.
Yes.
Climate change is a creeping thing. It's the frog in the water and then turn on the burner underneath. I'm more hopeful. In a sense, well, it's hard to say. I guess in the big picture, I would say overall I'm more hopeful in regard to asteroid prevention of asteroid impacts, simply because the first time we get hit, it's likely to be a small one, and it's likely to be in the ocean. So we're gonna be given a lesson,
And it'll get our attention.
It'll get our attention, and people will be serious enough to think, oh, that was a little bigger, or if that one was hit in the ocean, the hit on land somewhere, So we're going to have a lesson. With climate change, it is the frog in the water, does he die because he doesn't hop out because there's never a right time to hop out, So, but both of them are certainly geopolitical challenges, which is very interesting. Think of that from the big picture of life, philosophically, evolution. We are very, very slowly coming to understand that we are one life form on a planet. And there are real threats which affect all of us. It affects the life form, not us individually. We have to act as a cooperative life form to prevent some of these large existential issues. I mean, COVID was a pretty good example of a local one, a biological one, locally. But again, the whole tension between individualism or an individual action and initiative and freedom and everything, and public good and public health, for example, that was really brought out in COVID. And I think we got a C- or a D, as a world in terms of dealing with COVID. No, I'm not going to wear a damn mask, and all of that kind of thing. And, I'm not going to get vaccinated, and my kids, shouldn't. That kind of thing does not acknowledge the fact that we are a local life form, and there are issues which we either deal with collectively, successfully, or at some point there is the end.
Yeah, one of the most interesting aspects of science to me is that even though people think of scientists as being focused on the data, I actually find that it really helps illuminate the boundaries of my own humanity and the humanity of the people I work with and the organizations that we're in. And you can argue that science in some ways is a language or a story of how we make sense of the world. And then part of that story is also how we allow it to change us or the actions that we take. And so when you're interacting, science is a way to interact with the natural world. And when you're interacting with it, when a human's interacting with the natural world, inevitably our individual values and our social values and our fears and our hopes get mixed into the pot.
Yeah.
And each person is so different, right? So it becomes this really chaotic, but in some ways also, for me, a fascinating.
Well, you'll love it. I don't know how much more time we've got, but one of the things, if you want to look it up, many years ago, as I thought about these things from a philosophical perspective, I realized that what we are going through here in terms of human evolution, in terms of the evolution of life on Earth, is certainly replicated billions of times in the universe at large. We're not somehow unique. And even though life may be rare, with everything that we know is out there, I mean, there is certainly intelligent life elsewhere. This is something which undoubtedly happens around the universe when local life forms and evolution proceeds. And at some point, you're at the moment that I have come to call cosmic birth. We are in our human Earth Mother moment of birth. And whether we make it out the birth canal successfully, whether we make it into the larger and unlimited life or future, will depend upon how we deal with these collective issues at this moment in time. And we are the ones with the greatest agency, aside from perhaps natural events, but largely whether we make it through the birth process. Now, cosmic birth is dependent upon our understanding of ourselves as a collective life form at this moment in evolution.
So each of us can participate in the process of midwife.
Will be
and-
participating
We'll have
in it. Are participating in it, yeah.
And the challenges are clear, but what gives you hope that we're going to pull it together and make it happen?
I'm kind of neutral on it. I suspect that in the general case, it's stillbirth around the universe. It probably dominates. I think that this is a very challenging evolutionary instant moment in time that must happen in every life form that forms anywhere in the universe and reaches this point where the local environment provides. Think of the mother about to give birth. I mean, the mother gives birth through this process of violence. I mean, contractions, and it's triggered by too much or excessive demand of the growing fetus for resources and excessive production of waste that the mother can no longer handle. That combination triggers the birthing process. Here we are. Mother Earth is experiencing exactly that. And if we're going to continue to grow, which seems to be an evolutionary mandate, really, in all biology, it's a fundamental nature of biology, then if we're going to continue growing, the way to do that is to move out through the birth canal and move into the local cosmos. Mining of asteroids, the availability of sunlight, radiation for cooling. I mean, there's a lot of assets in space which are going to allow us to continue to grow if we make it successfully through that process. But in the meanwhile, a lot of those same technologies create everything from nuclear weapons to climate issues to, political conflict and AI, who knows, So, AI may ironically be the terrible answer to the Fermi paradox. Who knows? We don't know yet.
I feel like our podcast needs to be like 4 hours with you, but we just have a few minutes left. So I think we should hear your thoughts about Artemis.
I have a specific question
Sure, yeah.
tied to Artemis. So I think the current accepted theory of how the moon formed was that it was through a giant impact.
Yeah.
So I am curious, you were on one of the precursor missions for the moon landing, and now we just had one of the current precursor missions happen, and they're orbiting an object that was created by a giant impact that would have been catastrophic had humanity existed at the time.
Yeah.
So I'm curious if you could tie it all together, and what would you, like, if you were on that mission now, if you had been on that mission now, having done all of this planetary defense work, what would have been going on in your mind as you were orbiting the moon? And what do you wish the next set of astronauts, or this whole set of astronauts, to know?
Well, the big thing about Artemis that was really not there in Apollo is that Apollo was easily acknowledged as a one-off thing. It was the lunar landing, the first lunar landing. And even within the program, while I think there were 6 landings that were planned or whatever, Apollo 17 was the last one. We didn't do 18, 19, and 20. It was a one-off thing. It was actually a political goal. The United States and technology, we made it. And we were the first to land on the moon. Now, when you're looking at Artemis and the Artemis Accords, with the worldwide coming together on that, except for the Chinese, I mean, again, short-sightedness, it should be everybody. But unfortunately, there's some politics got in the way of that. Nevertheless, this is not a one-off. We're going back to the moon this time for permanently to be there, to stay there, to expand human territory. It's a little bit like sticking your hand out the birth canal. Not much. We got to follow it with the whole body. But
We're seeing the baby crown.
yeah, and by the way, I don't mean evacuating the Earth. That's as soon as people go into this cowboy mentality, that's not it. The human birth metaphor is the one to think of. And on the one hand, a 15-month pregnancy is not a good thing. Okay, so that's not a good model. But a birth where the child comes out and has an incredible, huge potential to be almost anything it can or wants to be, that's the future. That's the model that, to me, is the more legitimate conceptual metaphor for what we're all involved in. But it's going to be a challenge, but I think the Artemis missions are really the first real commitment to that kind of a future. Hopefully, as Artemis progresses, we all realize we're together. That the thing that I think is going to determine whether we're stillborn in this process or whether, in fact, we have that long-term future is going to be the recognition that we are one life. We are together in this. This is not an individual, rah, we're stronger than you or whatever.
I think that's a great note to end on. That's an inspiration for all of us, really.
Yeah, it is. And it all of the wonderful things of diversity and all kinds of people coming together is just the picture that I think we have to have.
Yeah.
The other picture of conflict and hate and whatnot doesn't work.
Yeah.
Power is not the only thing.
In many ways, as we're increasing the cross-section, the impact cross-section, because we're going from not just Earth, but also to the moon and eventually Mars, it's almost like we're also building more interdependence. So the stuff that we do now will become actually more important as humanity expands to other bodies in the solar system.
But as always, these things, as they get more and more capable and more powerful, become also more and more the other side of the coin is they become more threatened.
Cost.
Right.
Everything comes at a cost.
Yeah, and again, once you get powerful technologies like that, it gets to be a challenge how to handle it. Yeah.
Well, let's look forward to the future, and
all part of the final exam, right?
Exactly. Well, Rusty and Melodie, thanks so much. This has been really great. And again, it goes too fast. There's so much we could talk about, and you're so thoughtful, and you've been doing this for so long. I'm glad you retired.
Me too.
How many times have you retired?
5 or so. My wife keeps count.
Well, thanks, despite you being retired. Thanks for coming and talking with us and inspiring future generations.
Well, thank you, and good luck.
Great seeing you.
Thank you. Melodie, good luck. Enjoyed it very much.
And you viewers, thanks for joining us. We'll see you next time on Star Stuff.
This podcast was made possible by our members and donors. If you enjoyed this episode and want to support our nonprofit in making more digital education like this available, go to lowell.edu/donate. Thanks for listening.